this is the Chapter 9, Estimating the Value of a Parameter lecture video. This is the official Professor Thomas's lecture video, and we're getting into estimating the value of a parameter. Confidence intervals will be covered in this section. So let's look at 9.1, estimating a population proportion. And there are three different learning objectives. Number one, it is to obtain a point estimate for the population proportion. 2, construct and interpret a confidence interval for the population proportion. And 3, determine the sample size necessary for estimating the population proportion within a specified margin of error. So first, obtain a point estimate for the population proportion. So here we have the definition. A point estimate is the value of a statistic that estimates the value of the parameter. So for example, the point estimate for the population proportion is p hat, and that is x over n, where x is the number of individuals in the sample with a specified characteristic, and n is the sample size. So here we have an example of how to obtain the point estimate of a population proportion. It says the Gallup organization conducted a poll in which a simple random sample of 1,015 Americans 18 and older were asked, do you consider the amount of federal income tax you have to pay is too high? Of the 1,015 adult Americans surveyed, 458 said yes. Obtain a point estimate for the proportion of Americans 18 and older who believe the amount of the federal income tax they pay is too high. All right. Now, obviously, we will not be able to poll the entire United States, but by doing a sample of 1,000 of them, and it's random, we're going to get an estimation of how many people would say yes. So here we're going to get p hat is going to be 458 over 1,015, which is roughly 45%. And so that is our rate, that is the proportion, and that's how you would get your point estimate. Okay, and our point estimate is going to, it basically estimates the true population proportion. Like if we were to be able to poll everybody 18 years and up, the actual population proportion will probably be kind of close to this. All right, let's look at the second objective, to construct and interpret a confidence interval for the population proportion. And basically, we construct an interval for population proportion based on a guess along with a level of confidence. So the guess is the point estimate of the population parameter, and the level of confidence plays a role in the width of the interval. So we're going to build our confidence interval around the point estimate. So the point estimate will be in the middle of the confidence interval, and then we will basically create like a margin of error plus or minus the point estimate. And the wider the interval, the more confidence we are that the true population is within that interval. Now, if we make the interval, if it's not as wide, we will have a lower level of confidence. So the level of confidence kind of dictates how wide the interval will be. So here we have the definition. It says a confidence interval for an unknown parameter consists of an interval of numbers based on a point estimate. The level of confidence represents the expected proportion of intervals that will contain the parameter if a large number of different samples is obtained. The level of confidence is denoted as 1 minus alpha times 100%. So here, if, for example, we have a 95% level of confidence, our alpha would be 0.05, which implies that if 100 different confidence intervals are constructed, each based on different sample from the same population, we will expect 95 of the intervals to contain the parameter and 5 not to include the parameter. Alright, so first you must review what we know about the model that describes the sampling distribution of p hat, the sample proportion. The shape of the distribution of all possible sample proportions is approximately normal, provided that n times p times 1 minus p is greater than 10. The sample size is no more than 5% of the population size, and the data are obtained randomly. The mean of the distribution of the sample proportion equals the population proportion, and the standard deviation of the distribution of the sample proportion, which we call the standard error, is given by that formula there. The square root of p times 1 minus p over n. Alright, so because the distribution of the sample proportion is approximately normal, we know that 95% of all the sample proportions will lie within 1.96 standard deviations of the population proportion p, and 2.5% of the sample proportions will lie in each tail. So we're talking the inner 95%, and therefore we have 2.5% in the lower tail and the upper 2.5%. And 1.96 is that number, is that z-score that separates those values, the lowest 2.5 from the upper 2.5. So basically, all we do to construct a confidence interval is we basically figure out the point estimate, and then it will be plus or minus the margin of error. So this is actually one way that one can write a confidence interval. The margin of error for a 95% confidence interval for the population proportion is 1.96 times the standard error there, little sigma p hat. This determines the width of the interval. Notice that you have to multiply by the 1.96. That changes based on the confidence interval that we are selecting. All right. So here, to visually illustrate the idea of a confidence interval, draw the sampling distribution of p hat. Now create the slider that shows p hat minus 1.96p and p hat plus 1.96p. As p hat leaves the blue shaded region, the corresponding confidence interval does not capture the population proportion. Alright, so it kind of just depends. As we construct a confidence interval, and let's just say theoretically that p, the true population proportion, which is unknown, we want to know if it will capture, if the confidence interval will actually capture the true proportion, because that's its job. Let's move on. So the figure tells us that for a 95% confidence interval, 95% of all sample proportions will result in a confidence interval that includes the population proportion, while 5% of all sample proportions, those in the tails, will result in a confidence interval that does not include the population proportion. Alright, here we go. Let's illustrate what 95% confidence means in a 95% confidence interval in another way. So here it looks like we're going to simulate different confidence intervals based around a population of 0.7, and it looks like there's going to be 200 of them, and out of the 200 it looks like there's a few that turn out to be too small, where it doesn't contain it there. All right, but the great majority of them will, as you can see. All right. So it's important to be able to interpret confidence interval. So it's basically a 95% level of confidence means that 95% of all possible samples result in confidence intervals that include the parameter, and 5% of all possible samples result in a confidence interval that does not include the parameter. Sometimes one may think that a 95% confidence interval means that the confidence interval will capture the true population 95% of the time. And that's just not what it means. Okay. Probability describes the likelihood of undetermined events. All right, and there's different ways to describe it. So here we have whether a confidence interval contains a population proportion depends solely on the value of the sample statistic. Any sample statistic that is in the tails of the sampling distribution will result in a confidence interval that does not include the population proportion. And there's our margin of error. We can see how it's calculated. The value z sub alpha over 2 is called the critical value of the distribution. It represents the number of standard deviations the sample statistic can be from the parameter and still result in an interval that includes the parameter. Now there are some common critical values. So if we have to construct a confidence interval, a 90% confidence level, the critical value will be 1.645. We always take the positive one. This is how much the area will be in each tail. 95% confidence interval corresponds to 1.96, and a 99% confidence interval corresponds to a critical value of 2.575. Now, sometimes though, they may ask, hey, construct a 96, 97% confidence interval. You then have to be able to create the critical value, find the critical value on your own, and we will probably do an example like that. All right, so let's look at this example on interpreting the confidence interval. So when the Gallup organization conducted the poll introduced in the previous examples, 45.1% of those surveyed considered the amount of the federal income tax they have to pay is too high. The Gallup reported its survey methodology as follows. Results are based on the telephone interviews with a random sample of 1,015 national adults aged 18 and older. For results based on the total sample of national adults, one can say with 95% confidence that the maximum margin of sampling error is 4 percentage points. Determine and interpret the confidence interval for the proportion of Americans aged 18 and older who believe the amount of federal income tax they have to pay is too high. The point estimate is 0.451 and the margin of error is 0.04. The confidence interval is 0.451 plus or minus 0.04. Therefore, The lower bound of the confidence interval is 0.451 minus 0.04 equals 0.411, and the upper bound of the confidence interval is 0.451 plus 0.04. So now we will say that we are 95% confident that the proportion of Americans aged 18 and older who believe that the amount of federal income tax they have to pay is too high is between 0.411 and 0.91. So it's important to just say we're 95% confident that the proportion of Americans. So we're confident that the proportion is in there, but we can't say that there's a 95% chance that it's in there. All right, here is the formula once again, and again, it does depend on alpha. Alpha may change depending on the confidence level that is given, but this is it. And technology will calculate the confidence interval as well. The margin of error is right here. This is the formula for the margin of error. So p hat plus the margin of error and p hat minus the margin of error. So here looks like we have a problem, and we're going to construct a 95% confidence interval. So first we need to calculate the sample proportion based on our data, and this will be what we're going to use to estimate the true proportion. So right now we got 0.34, 272 over 800. And now it's time for us to calculate the margin of error. But we do need to check. We need to make sure that we have a nice sampling distribution, a normal distribution. And if it satisfies this, then our sample will be normal. And n times p hat times 1 minus p hat is greater than 10. So there are more than 1 million teenagers, 16 to 17 years age in the US. So our sample size is definitely less than 5% of the population. The independence requirement is satisfied. All right. Now, because it's a 95% confidence interval, when we calculate our z, our critical value, it is 1.96. So 95% is actually a pretty common confidence interval. And we simply do p hat minus, z alpha over 2 times that, and we're going to add it for the upper bound. This is our lower bound. We're going to add it to get our upper bound. The margin of error is 0.033, and we can now say that we are 95% confident that the proportion who texts while driving is between 0.307 and 0.373. Now the question is, well, how could you do this using technology? StatCrunch allows you to calculate confidence intervals as well, so we can look at that. It gives you it basically gives us the sample proportion, p hat, the standard error, and then the p hat plus the standard error and the p hat minus the standard error. So that's good. Let's look at doing the same problem using our calculator as well. We didn't try that yet. Let's bring up our Texas Instrument here. And all right, so we're going to create a confidence interval, but we're talking about for proportions. So we're going to go into stat. test, go over to test, and now we just kind of go down until we see prop z interval. One prop z interval, so it's alpha a, it's a. And here we put in our success is 272, and also it's 800. And our confidence level is 0.95, that's good. And there you have it. It gave us a point estimate of 0.34, but also the up top, that is our confidence interval. We can actually calculate the margin of error ourselves. We can add these two endpoints, divide by 2, we get 0.34 back. But if we subtract this and divide by 2, we would get the margin of error. Or another thing you can do is take that 0.34 and subtract it from the upper bound, and that will give you your margin of error. Or you can take 0.34 and subtract the lower bound. That will give you your margin of error. And they will be the same value. Alright, so if we were to increase the confidence level to 99, that will result in a larger margin of error, which would make our interval bigger. This is how you would do it by hand. We could do it in the calculator as well. So they tell you how to actually calculate the midpoint, margin of error, and all of that good stuff. And now the third objective, it is to determine the sample size necessary for estimating the population proportion within a specified margin of error. This is the formula you would need. N is equal to p hat times 1 minus p hat times z sub alpha over 2 divided by e squared. So let's keep going. Well, sometimes what we do is if we don't know what p hat is and we need to get the sample size, we need to get n, we'll let p hat be 0.5. So sample size needed for estimating the population proportion. And this is the sample size needed for estimating the population proportion. This is when p hat is unavailable. We would simply use 0.25. All right, now let's actually talk about how we can actually program our calculator for these values. Let's see if I have an old program that does this. I may or may not. Okay, looks like I don't have a program, but I can show how we could get a program to do this. All right, so we're going to call this program, let's see, in size. So I'll do in space. Oh, they probably don't want me to make a space. Okay, so no problem. Do one word. Size. In size. Having trouble finding the letters. There we go. Z-E. Hit enter. Okay, so basically the way this program is going to work is we're going to enter our confidence level. We're going to enter our our P, and then we're going to enter our margin of error. And it will then calculate in for us. So first, we need to prompt, we can just say, let's go back in the program, go over to display confidence level. We need quotes. I'll do alpha lock con level, or I'll just put C dash level. How about that? Yeah. C, and is there a hyphen? Maybe we can use a minus sign. Oh, there we go. Hold on. Easy. Get all of that. C and then level. Back to alpha lock. L. Let's see here. L E V E L. And let's do a question mark at the end. And then close bracket. Alright. Let's take off the alpha lock. So display confidence level. It's going to say confidence level, and then we're going to be waiting for them to input the confidence level. And we'll go back to program and do input, and we'll call it C. Alpha C. Next, we're also going to ask them, after that, we're going to ask them what's the P, and then after P, we want them to enter the error. Okay, so we'll just do, let's speed it up. Let's go to a prompt, and we're going to prompt them to enter in P. And we can always modify this code if it doesn't work the way we want. And also E. Okay. So the program will prompt them to enter P. They have to type it in, and then after that enter E. They have to type it in. And then we're going to have three variables. We're going to have the confidence, we're going to have the proportion, the margin of error, and then we're just going to use the program. So once we have the confidence level, we actually have to subtract. We have to convert it to alpha. So we're going to do 1 minus the alpha C, and we're going to store that in A. And then the next thing we got to do after that is actually take A divided by 2. Let's see, like for example, if it's 95, you got to enter in 0.95. We would subtract that. We would do take alpha A over 2. Let's see. And then we have to, let's get this right. So let's say we're dealing with 90%. And we subtract 90%, we're going to get 10%. And if we take 10%, half 10%, we get 0.05. All right, at this point, I know what we can do. Let's go into program, not program, stat. It's actually in distribute, isn't it? Second, distribute, inverse norm, and we're going to take the inverse norm of a over 2. But we want this value to be positive. That's the problem. So we need the absolute value of it. And I'm going to go into math. Number 1, the absolute value of inverse norm of alpha over 2. And then we're going to store all of that in Z, because we have our Z now. So store that into Z. And let's just kind of let's talk about why this works right now. Let's see. Alpha Z. I'm getting really slow at this. Alright, so when we do the inverse norm, let's say our confidence level was 0.90. We're going to subtract 1 from 0.90 and get the alpha, 10, and then we would do the absolute value of, then we would do the inverse norm of 0.05. That's the low tail. So it will be negative. And all we're going to do is make it positive and store it as Z. So our Z is good now. Now all we got to do is enter in the formula. And we do need the correct formula at this point. So n is equal to, we have our formula right here. It's going to be P, so alpha P times 1 minus P times Z, we just calculated that, alpha Z divided by, divided by E, the margin of error. And this is all good. And let's use the multiplication symbol. So I'm going to insert. Let's just make sure we're really we just want to make sure we're really multiplying there. So yeah, we will, and of course we'll test the program out. But now we're going to store all of this in let's store it as M. Actually, no. This is the formula for N, so we're actually going to store it in N. Alpha N. That's it. And now all we're going to do is display in. So what we'll do is we'll type in yeah, no sense in trying to doll it up. Display alpha n at this point. Whoa, alpha n, enter. And the code is complete. Now it's just a matter of testing it out and making sure that it works. And by the way, we didn't have to do absolute value of this. We could have did well, we could have just added a over 2 to the original a value. So, well, we could have did some weird things, and then we would have gotten the positive one. But this is, I guess this is the safe way to go. This is fine. All right, let's get out of our code. It's done. Now it's just a matter of testing it out. We need a problem to test it on, and it looks like we have a problem now. It says an economist wants to know if the proportion of the U.S. population who commutes to work via carpooling is on the rise. What size sample should be obtained if the economist wants an estimate within 2 percentage points of the true population with 90% confidence? Now, the 2 percentage point, that's the error, so we got to put that in as 0.02, and then the confidence level is 0.90, and then it looks like there's more. So for part A, the P is 0.10. All right, so here we go. Let's try this. We're going to go into Program, N size. It says, what is our confidence level? 2 question marks. So we didn't need a question mark. Maybe we should have had colon. So our confidence level is let's go back, 90. So we're going to put in 0.9. What is the P? Well, the P is going to be 0.10 in our case. So 0.1 is good. Enter. And then what is the E? Well, the E is 0.02. And we got 608.7. And they got 608.9. I'm happy with the way this turned out. It turned out good. Now, one thing about calculating in, and they're going to emphasize this in the slides, you always round up for our sample size. Now, even if it was 608.1, you just say, hey, we need an extra person in our survey. But here you clearly will round up to 609 because it's more than 0.5. But just as FYI, 608 point, anything more than 0.5 is you round to the next one. But we could also go low. If it was 608.2, the answer would be 609. So you round to the greatest integer always when it comes to the sample size for the program. All right. And I'm going to do one quick edit in our program. Here, I'm going to put in colons instead of question mark. And the colons are actually alpha colon then. Yeah, that looks better. If we run the code, confidence level, put it in as a decimal, P, put it in as a decimal, E, put it in as a decimal, and you will get the answer to that. All right, let's move on. All right, so point For part B, we don't know what p hat is, so we have to put in 0.25, and that's what we'll do here. So let's do the same program, but we just don't know what it is. Same confidence level, but p we don't know what it is. And then e we're going to put in as 0.02 again. And what we got is you need to survey 1,269 people. That is the minimum that you would have to survey. And that's how it works. Um, all right, let's go back to part B for a second. All right, and it looks like they're getting a different value. Let's see, 1.645. I find that really odd. Oh, no, no, no. Oh, okay, I see the problem. I see the problem. Yeah, we're supposed to put in 0.5 for P. Um, so let's do this again. Confidence level is 0.9. We put in 0.5, and E is 0.02. Okay, we got 1690. We rounded to 1691, and that's consistent with what they got as well. Although they're going to have to round to 1692 now. Our answer is more accurate than theirs because they round their critical value to 3,000 places, but our critical value doesn't get rounded off. Okay, this is section 9.2, estimating a population mean, and this is just like the previous section. However, we are talking about a population mean instead of a population proportion. And in this section, there are a list of different learning objectives that we are going to tackle. Let's start with the very first one. How do you actually obtain a point estimate for the population mean? And it turns out the point estimate is the value of the statistic that estimates the value of the parameter. And basically, we will be using the mean. The sample mean will be our point estimate. So we're going to build our confidence interval around the mean. The mean will be in the center of the confidence interval. Okay, now how do we actually calculate that? So suppose we have 16 different values, and these numbers represent miles per gallon of a specific type of car. We're simply going to add them all up and divide by the total number of 16 to get the average number, the mean of all of those numbers, and that's 28.1. So that's our estimation for the real population. Out of all of those 2014 cameras that were ever produced, we believe that um, it's near 28.1. We know it's not exactly 28.1, but it can't be too far off. All right, especially if our sample is a random sample. And another note here is that we've approximated um, our mean to one decimal place. You always want to take it out to one place, one more place than the raw data. So in our case, we actually got 28.1. Let's look at the second objective. This is called the student's t distribution, or sometimes just the t distribution, but sometimes you might see the word student's t distribution. So let's dig in and talk about what that is all about. So the student's t distribution, which sometimes we just call it t distribution. So suppose a simple random sample of size n is taken from a population that follows a normal distribution. The distribution of t equals the mean minus the mu divided by the standard deviation divided by square root of n follows the student's t-distribution with n minus 1 degrees of freedom, where x bar is the sample mean and s is the sample standard deviation. So let's look at this here. Use statistical software such as a Minitab or StatCrunch to obtain 2,000 SRSs of size n equals 5 from a normal population with mean 50, with mu 50 and a standard deviation of 10. Calculate the sample mean and standard deviation, the sample standard deviation of each sample. Well, basically what we're going to be doing is we're computing z and t for each sample. All right, so let's do that. And here are the histograms of each one. So notice that the histogram in figure A is symmetric and bell-shaped with the histogram centered at 0, and virtually all the rectangles lying between -3 and 3. In other words, z with n equals 5 follows a standard normal distribution. The histogram of t with n equals 5 is also symmetric, bell-shaped, and centered at 0. But the histogram of t has longer tails, so it is unlikely that t follows a standard normal distribution. This additional spread is due to the fact that we divided by s over the square root of n to find t instead of sigma divided by the square root of n. So now we're going to repeat this for sample sizes of size 10. Here it says repeat part A, and also we're going to do the same thing for t. Here we have that in A, it's symmetric and bell-shaped, centered at 0. Virtually all the rectangles lie between -3 and 3. So it follows the normal distribution. And the t-distribution, the student's t-distribution, it's also bell-shaped and centered at 0. But the histogram has longer tails than the histogram of the standard normal distribution. So one very important distinction must be made. The distribution of t with n equals 10 is less dispersed than the distribution of t equals n equals 5. We conclude that there are different t-distributions for different sample sizes. So in addition, the spread in the distribution of t decreases as the sample size n increases. In fact, it can be shown that as the sample size n increases, the distribution of t behaves more and more like the standard normal distribution. Alright, so here are some properties of the t distribution. The t distribution is different for different degrees of freedom. The t distribution is centered at 0 and is symmetric about 0. The area under the curve is 1. The area under the curve to the right of 0 equals the area under the curve to the left of 0, which equals a half. As t increases or decreases without bound, the graph approaches but never equals 0. 5. The area in the tails of the t-distribution is a little greater than the area in the tails of the standard normal distribution because we are using s as an estimate of sigma, thereby introducing further variability into the test statistic. As the sample size n increases, the density curve of t gets closer to the standard normal density curve. This result occurs because as the sample size n increases, the values of s get closer to the values of sigma by the law of large numbers. So here in this figure, we show that the t-distribution for the sample size n equals 5 and n equals 15, along with the standard normal density curve. This is what we have, and notice we have different shapes, different t-distributions there. So here in this third objective, we're going to be determining the t-values, and so Here we will be using this notation. Z sub alpha is used to represent the z-score whose area under the normal curve. Let's get back there. Hold on. Okay. Z sub alpha represents the z-score whose area under the normal curve to the right is alpha. And similarly, the T alpha represents the T value whose area under the T distribution to the right of T sub alpha is alpha. So it works the same way. We treat it as the same way. Now find the T value such that the area under the T distribution to the right of the T value is 0.10. Assume 15 degrees of freedom, and that is, find T sub 0.10 with 15 degrees of freedom. So if we were to draw this, the T distribution for 15 degrees of freedom will look like this. And then the area to the right is going to be 0.10, exactly 10% of the entire graph. And we're trying to find T sub 0.10. Oh, we'll be able to use a table for this. We'll go to the T distribution table. This is table 7. We find the degrees of freedom, and we also locate the area, and we can see where it matches at 1.341. And so we get it that way. Now, the question is, can our calculator handle this? Can we do this using technology? Well, some models of the TI-84 may not have this function. So let's see if yours has it. You go to second, distribute, and it's number 4, inverse T. All right, now, if you don't have the inverse T, there's a program out there that you'll basically just code it, and you'll create the program for inverse T, and then you'll just use that program anytime you want to use inverse T. So if I hit enter, okay, it's prompted me for the parameters that I separate by a comma, but I'm going to put on stat wizard. That way, if you have on stat wizard and you choose a stat function like inverse T, it's going to prompt me now. So I need 0.10, and my degrees of freedom we figured out to be 15. Now I'm going to paste this to the home screen. Okay, the top 10% is actually the top 90, so it is 1.34, but we should have gotten the positive one. So what we're going to do is recall this, and instead of putting in the top 10 is also the top 90%, and we get 1.34, and that's exactly what we were getting at. And they explain this as well. It's all pretty much more or less explained here, how we're talking about the area in the right tail. All right, let's proceed. The critical value of z with an area to the right of 0.10 is approximately 1.28, which is smaller than the critical value of t with 15 degrees of freedom. This is because the t distribution has more spread than the z distribution. All right, let's look at objective 4. It is to construct and interpret a confidence interval for the population mean. So constructing a 1 minus alpha times 100% confidence interval for the mu. So here we go. Provided sample data come from a simple random sample or a randomized experiment, sample size is small relative to the population size, and the data come from a population that is normally distributed, or the sample size is large. And here we have it. A 1 minus alpha times 100% confidence interval for mu is given by the lower bound, the mean, minus the student t distribution sub alpha over 2 times s over square root of n, and then the upper bound, we're going to be adding that t sub alpha over 2 times s over square root of n. And they also say that T sub alpha over 2 is the critical value with n minus 1 degrees of freedom. So the margin of error is that piece that we're going to be adding and subtracting from the point estimate. All right, so let's take a look and see what this problem is. The normality condition. So when the Gossip developed the t-distribution, he assumed that the sample data came from a population that is normally distributed. Most distributions are not exactly normal. So we need to verify that the sample data appear normal enough before using the t-distribution to construct a confidence intervals for the population mean. We have two options. Well, if n is less than 30, draw a normal probability plot to check the normality condition and a box plot to check for the outliers. If the data appear to be come from a population that is approximately normal, no outliers, then it is reasonable to use the student's t-distribution to construct a confidence interval for population mean. Option 2. This option relies on the robustness of constructing confidence intervals using student's t-distribution. An inferential method is robust if it is accurate despite minor departures from its underlying assumptions. And our particular assumption is this, that the normality of the student's t distribution there. So if n is less than 15, use the student's t-distribution to construct confidence intervals about a population mean. If the sample data are symmetrical with no outliers, the data should not be skewed left or right. This condition may be verified with a box plot. The median should be in the middle of the box and the whiskers should be of equal length. Alright, so if the size is between 15 and 30, use the student's t-distribution to construct a confidence interval about the population mean, provided that the sample data do not have extreme skewness or no outliers. And then finally we have this. You will use the t-distribution to construct confidence interval about the mean. And this even for the skewed distributions when the sample is larger than 30. And it's because of the law of large numbers, the central limit theorem. All right. So here it says the website Fuel Economy allows drivers to report the miles per gallon of their vehicle. The data in Table 3 show the reported miles per gallon of the 2014 Toyota Camry automobiles for 16 different owners. Treat the sample as an SRS of all 2014 Toyota Camry automobiles. Construct a 95% confidence interval for the mean miles per gallon of 2014 Toyota Camry. Interpret the interval. Alright, so first let's look at a normal probability plot, and this is something that we didn't really cover too much. So our examples it'll be assumed that it is a normal distribution. And here they're plotting it. It looks like the mean is slightly, or the median is off-centered. And the two whiskers are not of the same length. And also our sample size is not even that much. It's 16. But because 0.95 is greater than 0.94, it is reasonable to conclude that the sample data come from a population that is normally distributed. Keep in mind, we pulled a sample. Our sample is random. It's not always going to match perfectly. The box plot does not reveal any outliers. The requirements for constructing the confidence intervals are satisfied using option 1. All right, so it's time to proceed now. First, let's find the mean and also find the standard deviation. And now we're going to construct a 95% confidence interval. That means that alpha is 0.05, and when we divide that in half, we're going to get 0.025. T turns out to be 2.131. We got it from the table, so we needed that value. And now we're going to multiply that value by s over the square root of n, and we're going to subtract it from x bar and add it to x bar to create our confidence interval. And now we have it. Our confidence interval is 26.83 and 29.37. Now they're probably going to ask, hey, how could we have done this using technology, right? Well, there's a few ways, a couple of ways. Well, if we know the mean and the deviation, let's move to the next chart real fast here. If we know the mean and the standard deviation, we can use one thing, and if we don't know it, we can still do it. So let's do some examples of this for a second. So we are going to go into stat and then go over to tests to do confidence intervals. And because we're constructing a t-interval, it's going to be number 8. And now the question is our data in a list, or do we know the stats of our data? Well, let's do it like we know the stats of our data. Our data, we're going to have the mean we're going to set to be 28.1. Scoot that over a little bit. Our standard deviation is 2.38. Our n is 16. And our confidence interval, our confidence level is 0.95. Hit calc, and we get 26.832 and 29.368. Now, there was another way we could have done it. If we just had the data alone, we would have had to enter all the data in a list. Let's clear this list. We would have had to enter all 16 numbers, and then once that is entered, we would go into stat, test, go down to t-interval, choose data, list 1, make sure it's a frequency list, is either put 1 or leave it blank, and then hit calculate. And it would have given us the same value. So that's how you would do confidence intervals in this section here, okay? Let's move on. Determine the sample size needed to estimate the population mean within a specified margin of error. And here is that formula. This is the formula that will be used. And they say to round up to the nearest whole number, even if you get an n that's like 200.3. You just round that up to 201. That's how many you need to survey. All right, let's do a problem here. How large a sample is required to estimate the mean miles per gallon within 0.5 with a 95% confidence? Well, we have all of the values. 95% confidence interval is a 1.96. Notice we're using the standard normal distribution, not the student t-distribution. S was given to us. Let's see here. Well, we got 2.38 from the standard deviation of that sample, and then we're dividing by 0.5, which was that margin of error there. And it looks like we got 87.04, but we're going to round that all the way up to 88. All right, there was a lot done in that section. Let's take a look at some of the practice problems. All right, let's go to 9.1. All right, we have a gang of problems. All right, 34 problems. This is one of the bigger homework assignments. All right, looks like you have to kind of mix and match and figure out what each one might mean. Like the margin of error will determine that. Point estimate. I always have trouble matching those up the way they're supposed to be. There you go. All right, let's move on. If you constructed 198% confidence intervals based on 100 different random sample sizes of n, how many of the intervals would you expect to include the unknown parameter? I'd say 98. All right, it's pretty good, fair questions there. This is interesting. Um, compute the critical value that corresponds to an 84% confidence level. So that's the innermost 84%, which basically implies we got 16 on each side, which is 8 on each side. And so we're basically looking for 8%. And then we're just going to make it positive. So 8% is like negative 1.4. So I put 1.4. I would put 1.4. That's what I'm getting. Let's see if it likes that. Okay. Yeah. Now, how do we do that? Again, 84% is the innermost 84%, which basically means there's 16% left over for the two tails. And that's the alpha, 16%. You have to divide alpha by 2, which gives you 8%. So we're looking for the score, the z score that separates the top 8% from the rest. And we knew that the tail had to have 8% in it. But we're talking about the right side. The z has to be positive. Let's move on. All right, this is a pretty hefty assignment. Take your time on this. All right, let's take a look at 9.2. I would have thought 9.2 would have been more. Oh, it's 33 questions in total, 33 points there. Yeah, so both of these are some pretty hefty problems there. Click the icon to view the table of areas under the t-distribution. So we need 18 degrees of freedom, and then also the area to the right is 10. And we're talking about area to the right. So 18 and area to the right, 1.33 should be good. All right, let's move on. All right, so you have all the statistics here, and all you got to do is construct a 99% confidence interval. I would definitely use technology here, and that would answer the question pretty efficiently. Some of these questions are a little redundant. I may have to remove a couple of them. It's just too redundant. I mean, you don't have to practice doing the same kind of problem 3 and 4 times in a row. But all in all, it looks pretty good. So we're going to wrap this video up here. Hopefully this was helpful. And again, as always, if you happen to have any questions whatsoever on any of these parts of homework, feel free to reach out. Take care.